So we're going to talk now about the second derivative in relation to the first derivative. We've looked at the first derivative test and the second derivative test, and we've related them back both what they mean about the original function, but they also have that same relationship between each other. So the second derivative in relation to the first derivative has the same relationships as the first derivative does to the original. So we need to talk about that because you will be asked about some of those questions. All right, so we know we're going to talk about some of those. So if we know that the second derivative is equal to 0 or undefined at a certain x value a, then we know, just to review, that f of x has a potential point of inflection, and that's where the concavity switches from either to concave up to concave down, or from concave down to concave up. And f prime has a potential max or min. Relative max or min. So again, keep in mind that that's just because the second derivative is really just the derivative of the first derivative. So that's what's going on there. If the second derivative is positive, we know about the original to review. The original f is concave up. But what does it mean about the first derivative? If the second derivative is positive, then that means the first derivative is increasing. And if the second derivative is 0, the original graph is concave down. But what it means about the first derivative is that that must be decreasing. Right? Because now the relationship between this, the first derivative, and the second derivative, they're just kind of like one derivative away from each other. So now we're talking about wherever the second derivative is positive, the first derivative is increasing. Wherever it's negative, wherever the second derivative is negative, the first derivative is decreasing, and so on. Whenever the second derivative changes from positive to negative, the original has a point of inflection changing from concave up to concave down. On the first derivative, when the second derivative changes from positive to negative, the first derivative has a relative maximum. When the second derivative changes from negative to positive, it's the same idea here, but they're just the vice versa. So has a point of inflection changing from concave up to concave down. And then f prime of x has a relative minimum. So we're going to now try to make the connection between these two columns, and we can ask the question in both directions. I can give you stuff from the right column and ask you, about things about the second derivative. I can give you information from the second derivative and ask you about the first derivative. That's what this little section here is about. All right, so we're going to consider this function. Notice it's the derivative on the open interval to answer the following questions. So based on the graph of h prime of x, how many relative extremities does the graph of h of x have? So you would have to take a look at that graph. So I'm going to ask you to pause the video here for a second and get that graph on your calculator. Okay, welcome back. So let's take a look at it in decimals. You should be looking at something similar on your calculator screen. So we want to know about how many relative extrema does the graph of h have. So this is kind of just a review question. This is our graph of our derivative. We know that whenever the derivative equals 0, the graph, the original has a horizontal tangent line, which means it may be a max or a min. To be a max or a min, the sign change actually has to occur. The first derivative has to change from negative to positive or positive to negative. We see that that happens at 0. So based on that graph, we're going to say that since, and they want a reason, so since h prime of x crosses the x-axis only once on -5 to 5, then h double prime, I'm sorry, then h, we're doing h of x, sorry. Then h of x has only one relative extrema, or we want to say extremum, the singular, on the interval. The next question. Based on the graph of h prime of x, how many points of inflection does the graph of h have? Give a reason for your answer. So when we want to talk about points of inflection for f, we're going to have to say that if we have the graph of the derivative of h prime, we want to say that first we want to look at what happens on f double prime. So because that's kind of what we know. So f of x has, or h of x has a point of inflection when h double prime changes signs, right? So if the second derivative changes signs, then we'll have a point of inflection from either way. So now we can look back to our chart of what that means on f prime. Well, if there's a change of sign on the second derivative from negative to positive, then that means that h prime has a relative minimum or a relative maximum. So based on that graph, how many points of inflection does the graph of h have based on the graph of our derivative? We have to look for, if this is our derivative, every time there's a maximum or minimum on the interval. So I see 1, 2, 3, 4, 5 times there's a maximum or a minimum on the derivative. Okay, so we'll say h of x has a point of inflection when h double prime of x changes sign. If h double prime changes signs, what does that mean about the derivative? Because that's what we're looking at, the graph of the derivative. Whoops, I don't need the comma there. I need the comma there. Then that means that h prime of x has a relative, oh my gosh, and that occurs 5 times. Okay, so again, this thinking can get a little tricky sometimes, especially the first couple you do. So you got to really try to keep everything straight. These charts will kind of help you organize your thoughts. Okay, last one is find the equation of h double prime of x and then graph it on your calculator. Explain why the graph of h double prime of x confirms your response. So we're just checking to see if we knew what we were talking about there, right? So I'm going to pause the video, or you should pause the video here. Find the derivative of h prime to get h double prime, graph it on your calculator, and then come back and see if you got it right. So this is what you should have gotten for your second derivative. And we want to confirm what about question 2. So we want to confirm points of inflection. So we know on second derivative, point of inflections on the original function occur when the second derivative changes from negative to positive or positive to negative. So I'm looking for those x-intercepts where it actually crosses the x-axis. We want to see how many of those we have. So if we look at the graph of the derivative, that's this. You should be seeing that on your calculator. It crosses on that interval, crosses the x-axis 5 times. Whoops. So you want to write that out. The graph of h double prime of x crosses the x-axis 5 times on the interval -5 to 5, which means H double prime changes signs 5 times. You got to state that. You got to make that clear. You can't just say it crosses the x-axis. You have to state that H double prime changes signs. That's how you know you have a point of inflection, which means f of x has 5 points of inflection on the interval. All right, so here's a chart that we can make that will help us. It just sort of, it looks like a lot right now, but it could help us keep track of stuff, how they all relate to each other until you kind of get used to this. So when f is increasing, the derivative is positive. When f is decreasing, the derivative is negative. If f of x has a relative maximum or minimum, f prime of x changes signs. You can't say it crosses the x-axis. You have to say it changes signs. You may have to say it crosses the x-axis, which means it changes signs, right? If f of x has a point of inflection, f prime of x has a relative max or min. If f of x is concave up when f double prime is bigger than 0. F of x is concave down when f double prime is less than 0. F of x has a point of inflection when f double prime of x changes signs. Again, you have to say changes signs. F of x is increasing when f double prime is positive. So this is now the relationship, like these are like one derivative away. So we know when the first derivative is decreasing, f double prime is 0. The first derivative has a relative maximum or minimum when the second derivative changes signs. Again, you got to say changes signs, not just crosses the x-axis. F prime of x has a point of inflection when f double prime has a relative extrema. So a relative max or min. F prime changes from negative to positive when f has a relative minimum. So that's a little bit of review. The derivative changes from positive to negative. That means that f has a relative maximum. F prime of x, so the derivative has a relative maximum when f of x has a, no, this should be an f double prime here. This is a typo, sorry. No, I want to say here that when the derivative has a relative maximum or minimum, we know that on the second derivative, there's a 0. It crosses the x-axis. It changes signs, the second derivative. So that means that f would have a point of inflection. Sorry. F double prime changes signs from positive to negative. That means that f prime has a relative maximum. That's because they're one derivative away. And the last one, if the second derivative changes from negative to positive, the first derivative has a relative minimum. So we took that relationship between first and second derivative, and we really added in another step here. So you've got all this stuff to consider, and notice the arrows go both ways. So I could tell you something from the right column, and you should be able to make the conclusion to the left column. So this is something that we're going to do in class here.